Okay, so I'm assuming that you read the problem. Now remember, they say that the population has some parameter, in this case 12% own red cars. And we're just going to test that. And how do we test that? We take a simple random sample and we look at the statistic on that simple random sample, and is that close to the parameter, 12%? And if it isn't close, how far away does it have to be in order for us to say, okay, we don't think that this is actually true? All right, so that's just kind of an overview of these types of problems. So here we go. Null hypothesis is no change. It doesn't matter if you're in the Phillies parking lot or not, you're always going to have 12% red cars. Now, we think that it's going to be higher. That's our alternative hypothesis. All right. Now, in this problem, you might have been confused because you're like, well, what's the alpha level? If there's no alpha level, you just go with 0.05. Okay, so that's just kind of a standard thing, and that's perfectly okay to do. So we're going to use a one proportion z-test in order to test whether 12% of people really own red cars at a significance level of 0.05. Now let's do the rest. Okay, so we can ensure random. It took a simple random sample of 210 cars. It says it right in the problem. Normal, the sample size times the parameter and 1 minus that parameter. They both give us a number bigger than 10. And independent, we just have to have over 2,100 cars. 10 times this value there, the 10% rule. And they actually say in the problem, I think there's 21,000 cars in the parking lot. So we're good on that. All right. So our sample proportion, that's p hat, is 0.1667. How do we get that? Well, we do division, which is 35 out of the 210 cars. That's how we get that number. All right. So we get a z-score, which we call a test statistic, and it's our observed value. Let's see, our observed value right here minus the parameter over standard deviation. Whoops, I forgot about the standard deviation. How do we figure that out? Okay, remember, square root of 0.12 times 0.88, right? Whoops, that's kind of messy. And divided by how many we took. Oh, 210. That is our standard deviation. So that goes underneath. And let's see what that number is. There it is. Now all that junk turns out to be 2.081. Now right away, I look at that number and say that's 2 standard deviations above what it should be. Now that indicates to me that it's pretty far up there. So our p-value, so we do normal CDF for this value, negative 1,000 to 2.081 normal CDF, and we get an answer of, this gives us an answer, a p-value of 0.0187. So that is our p-value. So what does that tell us? It tells us there's only about a 2% chance that we would get a statistic this high if the actual value in this parking lot was 12%. So we're going to reject the null hypothesis and say, yes, we think that the parking lot has a much higher proportion of red cars in it. Okay? So there you go. Okay, this one might have been a little bit confusing because we're combining a 95% confidence interval, if you remember what that means. We're 95% confident that the true proportion for this population is somewhere between those two numbers. And we're using that in conjunction with our significance test, which is at a alpha level of 0.05. Well, I'm going to assume that you read this problem, And it turns out that this 0.44 is contained within that confidence interval. So if that's the case, we cannot reject the null hypothesis. Okay, so it's pretty straightforward. If our parameter is contained inside this interval, we cannot reject the null hypothesis. And that seems to make sense because we're 95% sure of that. Okay, let's do letter B. So in letter B, they say, well, let's just figure out the p-value anyway, just to see what would happen. So the sample proportion is, we took 186, supported our candidate out of 450 people that we asked, and that proportion is 0.4133. So again, we're saying, well, how likely is that if the true proportion was 0.44? Now, we do our test statistic, or a z-score. It seems like the book is saying you could do almost either way. But we take 4133, what we observed, minus what they say the parameter is, the true proportion estimate for the population. And we need to get the standard deviation. So remember, we always use the population, right? 0.56, and divide that by 450. Now, do all that stuff, and we get a value of negative 1.14. So it's underneath, so it's 1.14 standard deviations below the average. All right, now, let's remember something. They were testing, the hypothesis was what? HO was the fact that the proportion was 0.44. The alternative hypothesis is that it's just different than 0.44. So this is called a two-tailed test. Now, if we did this, let's just take a look at what this looks like. It looks like this. Here's where you say 0.44 is, somewhere there. And we come down here 1.14 standard deviations below that and say, well, what is that? Oh, right, we got to do normal CDF. So if we do the normal CDF for negative 1.14, we are going to get a value of about 0.127. 0.127. So that is this area right here. This area is about 13%. Now, we might use that if we were saying, what's the probability that the percentage is lower than 0.44%, okay? But now we say, well, it's above or below, so these are going to be, because everything is symmetric, right? So below would be down here, 12.5%, and there's also 12.5% chance that it's that much or higher. So in a two-tailed test, we combine these two. We add those two together, and it turns out that you get a value of 0.254. So that's our p-value. P-value of 0.254. Okay. Now, that's a lot bigger than 0.05, which relates to the answer in question A, which was we have to fail to reject the null hypothesis. So the conclusion might be something like, well, if the proportion of voters that support the candidate really is 44%, the probability of getting a sample that is at least 1.14 standard deviations higher or lower, right, because we're just talking about is it different from that, is about 0.25, almost 1 in 4 chance that we would get a sample with that kind of a proportion. Fairly likely. Okay, but we don't accept the null hypothesis, we just fail to reject it. Okay, there it is. See you tomorrow morning, bright and early. Bye.